Big discoveries often come from the need to solve a problem. But sometimes, new materials are a solution looking for a problem to solve. Bulk metallic glass, also known as amorphous metals, have some really cool and amazing properties. They are strong, flexible, and can be used in ways conventional metals can't.
Much like aluminum at its start, amorphous metals have lots of potential, but are still kind of exotic. Imagine dropping your cell phone and having it bounce right back into your hand.
Today, bulk metallic glass, or amorphous metals, have emerged as a new class of materials looking for potential applications.
So in the 19th century, you wouldn't have seen common uses for aluminum, like, for example, in the bike racks here or in soda cans that you would drink. It was an exotic metal, and it was used for largely ornamental purposes. For example, it capped the Washington Monument. People used it for dinnerware. It was extremely expensive to make. And that all changes in the late 19th century, early 20th century, with the development of a process that made aluminum cheap to make. So amorphous metals are also a kind of exotic material. You see, the most common example I've seen is in golf club heads, but they obviously have kind of broader application. They have that trampoline effect, that there must be other ways in which we can use them. And it's a similar process to when aluminum first was able to be cheaply made. It was kind of a material in search of an application.
Metallic glasses were invented at Caltech by my advisor's advisor in the late 1950s, and his name was Professor Paul Dway. And so he was studying an interesting phenomenon of being able to cool metals without them crystallizing. And then my advisor, Bill Johnson, took over that group in the 1970s, and in the early 1980s developed bulk metallic glass, which is this alloy, which most famously is known as vitrolloy. Now we're in a third generation of metallic glass, which involves the design of new alloys and injection molding technology, which is similar to what's used in plastics. And now we're really seeing the widespread explosion of the technology in industry. There are many synonyms for bulk metallic glass. Metallic glass is a synonym. There's also amorphous metal. There's undercooled metals. There are liquid metal, flex metal, non-crystalline metals. There are glassy metals. All of these descriptions, they refer to the broad family of metal alloys which exhibit the property of being glass. The true advantage of using metallic glass compared with titanium, which is its closest similar crystalline alloy, is that metallic glass, being a low melting temperature material, can be injection molded into parts like plastic. Except when you take a metallic glass out of a mold, by the nature of it being frozen into a glassy state, you get properties out of the part that are similar to titanium or steel. That is an absolute revolution in the way that you make small, complex metal parts.
These properties make them ideal for applications here on Earth. For example, the trucks on Nina's skateboard. Check this out. This plate on the left is made of steel. The one on the right is bulk metallic glass. Now watch the bouncing ball. That's kind of fun, but what gives it that bouncy quality?
The trampoline effect is the resilience of the material. You are measuring the resilience of the material, and this bouncing is called the coefficient of restitution is what you're measuring. So a ball bouncing on a surface measures coefficient of restitution. The material property which gives metallic glass this high coefficient of restitution is called the resilience. And the resilience of the material is the square of the yield strength divided by 2 times the Young's modulus. Metallic glasses have an extremely high yield strength and a very low Young's modulus, so they have a skyrocketed resilience.
And what golfer wouldn't love to smack a drive further down the fairway? Clubs with bulk metallic glass or amorphous metal components can give golfers some advantage.
When you hit a golf ball with a metallic glass club, most of the energy of the club face goes into the ball. So what this means is that you can hit a golf ball with very little energy loss and the ball goes very far. Of course, this would make golf courses obsolete if every player could just hit it to the green in one shot. The USGA has decided to limit the performance of the metals that go into the golf clubs to prevent pros from being able to shorten golf courses. And that's really just economics so that golf courses that exist don't become obsolete as people can hit the ball further.
But engineers at places like the Jet Propulsion Laboratory are looking to the future, beyond Earth's boundaries.
So one of the things we do here at JPL with metallic glass is we try to identify applications for metallic glass that could benefit spacecraft or rovers. So we've been working for a long time trying to develop small, low-cost mirrors that can be made for space telescopes. One of the things we've also been looking at is trying to develop cellular structures which are useful for making debris shielding on spacecraft. We've developed is metallic glass cellular structures. In this case, we've taken the shape of a common egg box and we've made it into a metallic glass through a forging technique. And then we can weld these egg boxes together into larger structures. And then we can hit these with hypervelocity particles, simulating an impact of debris with a spacecraft, which metallic glass is a very hard material, which makes it a perfect material for using as a spacecraft shield. These are two plasma arc melting systems. Now, most metallic glasses are based in elements like zirconium and titanium. And zirconium and titanium oxidize heavily, so you have to melt them in inert environments. So what we have here, these are basically vacuum chambers where we take out all the oxygen and we replace the oxygen with argon, which is inert. And then what we do is we have a constant DC welding supply, which is hooked up behind us, and this DC welding supply feeds into these two arc melters, and we're allowed to do plasma arc melting. So right now I'm putting 168 amps at 12 volts through a sample, and you can see in the infrared camera that I'm melting a piece of pure titanium with the arc melter. This is a FLIR infrared thermal camera, and we are looking into the chamber through a vacuum-tight germanium window. And at the wavelengths of my camera, germanium is transparent at those wavelengths. So we are able to film through the chamber through an optically opaque window. So once I'm finished melting with the titanium getter and I've gettered the environment, now I'll start melting a metallic glass sample, which is back here in this well. And so what I do is I just turn the arc on and move it around to try to homogenize the melt until it begins to flow. And once it begins to flow, it will melt and mix itself. So good. Now, one of the cool things that happens is when I turn off the arc, you see the liquid moving around? That liquid is going to start to cool rapidly because the liquid is touching a water-cooled copper hearth. So at about 100 degrees a second, that liquid will cool. And because of the way the liquid is designed, it should cool into glass. It should not crystallize. And we should be able to see that from an infrared image. So here I'm going to turn off the arc, and we're going to watch the ingot slowly solidify and cool. And we see no crystallization events. So that means that the ingot has frozen into a bulk metallic glass. But you can see that the ingot has no trace of crystallization on the surface, has a perfect mirror finish, which is cooled natively. So this is the high surface tension of the metallic glass and no evidence of crystallization. So one of the things that we do with metallic glass here at JPL is we cast metallic glass into gears, and we make all kinds of gear components out of metallic glass. So the arc melter is one of our pieces of equipment that we use to make gears. And in this case, we're going to be making this pinion gear, which is a rod with gear teeth around it that fit inside a small robotics gearbox. So the way that we do that is we melt the metallic glass in a crucible, and then we push a foot pedal to apply suction pressure to the liquid. And that suction pressure sucks it into a mold, which is sitting below the hearth, which looks like this. And that mold has a gear inside of it, a gear mold inside of it. So what I'm going to do is I'm going to melt the ingot, and then we're going to suck it into a mold to form a gear. And there it goes. Compared to the way that these gears are manufactured in industry, this has to start as a billet of steel that's this big, and it has to be machined into the shape of the shaft, and then the teeth have to be hobbed, which is a technique that's used for making gears. With metallic glass, we can actually cast these in one single step into a mold that's reusable, so that we can make thousands of gears out of one single mold. And yet we get wear properties that are superior to steel from the metallic glass gear. One of the cool things about metallic glass is that metallic glass, like oxide glasses, can be thermoplastically formed and can be blow molded. So instead of melting the metallic glass and injecting it into a mold or sucking it into a mold, you can actually just heat a metallic glass to a much lower temperature, typically around 400 degrees centigrade, where the viscosity of the metallic glass drops dramatically, at which point you can then form it, or you can pressure mold it, or you can vacuum form it. So I'm gonna take a rod of metallic glass and I'm gonna stand it up in the chamber, and we're gonna push on it and hopefully form it into a plate.
These metals show remarkable corrosion resistance. What are the potential applications?
Widest spread uses of metallic glass in industry right now are in the coatings and in the ribbon area, used in the oil and gas industry for hard banding and for corrosion resistance. So you can use a thermal spray coating technique to apply a metallic glass coating over a drill bit or over piping or over some mechanical component that may be exposed to abrasive wear or exposed to chemicals which may degrade it, so corrosion. And metallic glasses are very effective material at stopping corrosion and stopping abrasive wear. Metallic glasses also typically have a very strong passive oxide layer. That passive oxide layer tends to prevent corrosion from initiating. Metallic glasses are great materials to use in structural coatings. So metallic glasses have unique mechanical properties, and as we've demonstrated, they have unique ability to be processed into parts. So about 5 years ago, we started trying to develop gears for our future Mars rover using metallic glasses. And the reason we did this is very specific. The gears that are on our current Mars rover require wet lubricant to lubricate the gears, and that takes power. We would like to be able to use gears that don't require wet lubricant and that can run with just dry lubricant. We would love to use ceramic gears, but the toughness of ceramics is too low for us to feel confident using them as gears. Metallic glass sits in the property space between ceramics and steel. So what you can do is you can make materials that are very hard, but that are also 100 times tougher than ceramics. This is JPL's Mars Yard. And so the Mars Yard serves several functions to support our robotics operations on Mars. So what we have here is the flight backup of the Curiosity rover, which is basically the exact same rover that's on Mars right now. So this is our test bed where we try out new software, we try out software upgrades, and we give it commands. So what we can do here is we can rearrange the Mars Yard to simulate the environment that's around Curiosity actually on the surface of Mars.
Amorphous metals represents in many ways this kind of ideal pairing of the kind of thinking we do in the humanities and the kind of research we do in material science. When you try to solve problems that aren't necessarily drawn from the market, sometimes you can have problems in the market that you didn't think of that all of a sudden get a solution. So I think that sometimes we're a little short-sighted in that we're constantly looking at, well, how can we make this material have an application now? And this kind of short-term horizon, I think, has limited us in many ways in the way that we involve materials in society. It would be nice to have a kind of long-term perspective on these materials. And the space program is a great example of where you have a long-range goal. You're not talking about coming out with a product line in a year or two. You're talking about doing something a decade or two in the future. And that long-term perspective can really help.
It's one of the amazing things about working at NASA is that sometimes you work on projects that you know will not reach their intended science destination until after you're dead. You really work on the time horizons of mankind here. These projects, they transcend your own lifetime. It takes a certain kind of mindset to understand the importance of that for humans. And exploring space is one of those things that we're doing not for us, we're doing it for future generations.